Okay, so as we run the code, we can see there is some non values coming here, non value or not a number. So why it is coming here? So to understand it, let's remove this, sorry, remove this portion and see how our values are converging. Okay, now let's run from, okay, let's clear the workspace first. Okay, then run to end. So this is my initial guess, count equals to 0, then count equals to 8. So as you can see, after some iteration, after few iterations, the value is converging into 4, and the value is so less, the EA is becoming 0. Okay, slowly it is going towards none. So that means I don't have to go up to 8 iteration to find the root here. Okay, so instead of using count as our condition, I can use this EA, our error, as the condition. That makes more sense, right? So if I use this error as my check here, so EA, that is my absolute error, as long as the error is greater than, say for example, 1 e to the power minus 8. Okay, so that is 10 to the power minus 8. As long as EA is higher than that, I will keep running this loop. Okay, otherwise I'll break out from this loop, so I can ignore this count option. I don't need this count option. But since I am using a while loop, I have to initialize my EA value. Let's initialize it as 100, something greater than this value, so that this loop runs. Okay, so let's start from it here again. So x0 x1 count is not it. Now as you can see, so I start from here. At first the EA was 100. Okay, the next step the EA was 25, and this was the x0 is 5.5, x1 is 5, and x2 is 3.97. That is our first iteration output. Okay, then goes to the next iteration. We perform the next iteration and we get a EO value of 0.6%. Okay, and these are my new estimates: 5, 3.97, and 4. 4 is the new estimate from this iteration. Then we go to the next iteration. From the third iteration, I get 0.02%. As you can see, the error, the approximate error, is dropping significantly. Okay, and the output, it is again 4. So we can see that our iteration is actually converging towards 4. Okay, so and the last step, as you can see, when we get to error value of 10 to the power minus 11, that is the last step. Okay, so all the x0, x1, and x2, our final iteration was 4. That means this 4 is one of the root of our equation. Okay, understand this portion first. So our fx was like x cube minus 13x, okay, minus 13x minus 12. So this has 3 roots. Okay, this has 3 roots, and from this curve, whatever the curve shape was, as I was assuming this kind of parabola like this, I was honing into this portion. I was actually focusing on this portion, and from this we have found that 4 is one of the root. Okay, one of the root of this 2 equation, and it has 2 more roots. Okay, so using this approach, using this iteration, I have been able to find one root. Now what about the other 2 roots? Okay, so for finding the other 2 roots, I will go the same way, but with slight modification I have to make in this code. Okay, so what modification, what can I do? Okay, so let's keep it here. Okay, so to understand that, first we have to incorporate some other things that was introduced in the last lecture. Where was those things? Yeah. Okay, so as you can see, this is the way to represent a polynomial. This is the way to represent a polynomial. Now using this polynomial, that was our initial polynomial was this, and we have found one root of that polynomial. Okay, so come here. So the polynomial that we have now, say this is x cube minus 13x minus 12, and we have found that 4 is a polynomial of this. So that means x minus 4 is a factor of this polynomial, is a factor of this polynomial. Okay, so in the next iteration I don't need to do it I don't need to find the root of this polynomial again. What I have to do, I have to factorize it in such a way that, because I have already found this polynomial, sorry, I have already found this root, I have to look into the other two roots. That means from this third order equation I have to convert it into a second order equation now. Okay, I have to convert it into a second order equation. So how do you do it? Say now, for example, if you come here, so our original poly, let's define. So polynomial was this, just p for now. It was 1, 0, minus 13, minus 12. This is my original polynomial, and the root that we just found, that is x minus 4. So this is another polynomial. This is my root 1. Let's name it as r1. So what should be the polynomial of r1? This is 1, right? This is 1, minus 4. 1, minus 4. So let's write it here. My r1 is equals to 1, minus 4. So if I do the convolution of p, r1, so what should I get? 143. What does it mean? 143. So it is returning 143. That means my new polynomial, let's say p2, is equals to x square plus 4x plus 3. Okay, this is my new polynomial. Okay, now as you can see, this is a second degree. Okay, so from this new polynomial I have to find the roots of this polynomial now. Okay, I have already found the roots of this polynomial. I have found one root of this polynomial. Then using this root I have to remove this portion. Then after removing this portion I get this polynomial. Now I have to find root of this polynomial. Is it clear? So I can do it in the similar way. So x square plus 4x plus 3. For now let's just copy it. So let's just copy it now. Okay, so as you can see, when I am creating a polynomial like this again and again, this makes less convenient. This make it less convenient. I have to check it again and again. So for now, okay, let's keep it here. I use this symbolic function now. That will make it more easier. So the new polynomial was x square plus 4x plus 3, right? X square plus 4x plus 3. So this is my new polynomial. So let's define it here. It is better I clear the workspace. Okay, so this is my new polynomial. Okay, so this is my initial guess. Let's keep it the same guesses. Okay, and I don't need count anymore. I can just comment it here. So this is my EA. This is everything, and I am using this function. Okay, let's name it f2 for. Okay, so f2, okay, then f2. Okay, so everything is same. Okay, let's see how it happens. So okay, as you can see, okay, let's do it now. As you can see, my first iteration EA was 600. Okay, this was 5.55 and minus 1. That was the new point we calculated. In the next iteration, in the second iteration, the EA becomes 0, directly becomes 0. Okay, and it is giving me minus 1. So minus 1 is my next root. Minus 1 is one of my root of this equation. Okay, this is the root of this equation. That means this is also the root of this equation as well, because I have factorized it. So minus 1, that means I have a new one, that is x plus 1. This is another factor of this equation of this polynomial. So I have found 2 factor of this polynomial, x minus 4 multiplied by x plus 1. I need another. So I have found one root, I have found another root, that is minus 4. I need another one. What I have to do? I have to factorize it again. So let's come here. So 143. So let's name it P2 is equals to 1, 4, 3. Okay, and my R2 is equals to 1, that was plus 1, right? That was plus 1. Okay, now I want to perform the same deconvolution operation with P2 R2. So what do you get now? 1, 3, 1, 3. So 1, 3 means what is my new 1, 3? So the equation becomes x plus 3, x plus 3. So I have already found this. That means the root of this equation is minus 3. Okay, so what I am getting here is that first I got my first root, that was identified as 4. The second root was identified as minus 1. The third root we have identified as minus 3. Okay, so I hope that it is actually clear to you now. That means at each iteration, start from the first step, start from this step where we started. So using this step, I can find one root. Then I have to, after I have found one root, I have to perform deconvolution. Okay, to reduce the degree of the polynomial. Then I can perform it again. Okay, then reduce the polynomial again. So like this way, an iterative way, I have to introduce it in my code again. Okay. Okay, so 1, 3. Come here. As you can see, if this is my equation, we can write this original one, this polynomial, as x plus 1 into x minus 3 into x plus 3, like this way. Okay, this is the this is another way of representing a polynomial. So we have actually calculated like this way, we have actually found like this way. Now the last thing, one other thing you can check, say for example, if you use the function roots is a function, this is a built-in function in MATLAB. Our original polynomial was this p, right? So if I calculate roots of p, as you can see, I think I have removed the p. So let's just name it as 1, 0, 1, 0, minus 13, minus 12, This was our original polynomial. And if I use this roots function in MATLAB, it automatically gives me 4 minus 3 minus 1 that we have struggled so much to calculate. Okay, so I hope this is clear, this concept is clear, how we can use this Muller method to calculate the roots. Okay, let's finish it here.